Hi, this is the lecture 2 of molecular orbital theory, right? So, in lecture 1, we have already understood how in molecular orbital theory, how atomic orbitals interact to give you molecular orbitals, right? And molecular orbital theory basically tells us that when atomic orbitals combine, right, they form molecular orbitals, right? And we have already seen that the number of molecular orbitals formed, right, due to overlapping or combination of atomic orbitals is equal to the number of atomic orbitals. That is, if two atomic orbitals are combining, they will form two molecular orbitals, right? And in the previous video lecture, we have already understood what is an antibonding molecular orbital and what is a bonding molecular orbital, right? And we have seen that bonding is due to bonding molecular orbital, right? And antibonding molecular is antibonding. Antibonding means it will oppose bonding, right? And what is the reason? The reason is that in bonding molecular orbital, the electron density is high between the atoms, right? Between the nuclei of the atoms, the electron density is high. This electron density will hold the two atoms together, right, and reduces the repulsion between the two atoms, because electron density or electrons will act as a shield between two nuclei, right, and repulsive forces would be low, right, and attractive forces would be high. If attractive forces are high, we know the energy of the system will reduce, right, because attraction will release energy, thereby reducing the energy of the system, right. And in case of antibonding molecular orbital, the electron density between the nuclei is less, right, and the electrons will spend most of their time away from the space between the nuclei, right. And we know that this antibonding molecular orbital is smaller because it is formed by destructive interference of waves, because orbitals, we know, are nothing but waves, whereas your more bonding molecular orbital is a bigger orbital, right, that is formed by constructive interference of waves, right. Now let's dive more into these bonding and anti-bonding things, right. So till this point we are now clear about the basics of molecular orbital theory. Now we'll again see the bonding and anti-bonding molecular orbital, and we'll see how bonding molecular orbital will lead to stability, right. We'll see it mathematically now, right. Earlier we have seen that if these are two waves, right, if suppose these two waves combine, right, constructively, they will form a bigger wave like this, right. And if psi A is amplitude of one wave, psi B is amplitude of another wave, the amplitude of this wave is psi A plus psi B, right. And we know that psi is what? Psi represents the amplitude, right. It's the wave function psi, and wave function gives us most of the information regarding the wave, right. And its solution is obtained from Schrodinger equation, right. You need to check wave mechanical model of atom to know more about this, right. Since psi represents your amplitude, right, we know, we have done this in atomic structure, that psi square, using psi square we calculate the probability of finding the electron in the orbital, right, and using the different values of psi square we build electron clouds, and electron clouds are nothing but atomic orbitals, right. So psi square mainly tells us the probability, right, it represents the probability of finding the electron in the orbital, right. So this is, if I take for individual waves psi A square represents the probability of finding the electron in this orbital, right. Similarly psi B square will represent the probability of finding the electron in this orbital, right? This orbital is represented by a wave, because orbital is nothing but a wave, right? So if we have this bigger wave, right, whose amplitude is sum of these two amplitudes, psi a square plus psi b square, so probability of finding the electron in this bigger wave, right, which represents a bigger orbital, right, would be psi a plus psi b square, this, right, and this is for constructive interference. Similarly, if we talk about destructive interference, right, for destructive interference, we know that the orbital that is formed by destructive interference of waves is a smaller orbital, right? And how do we get it? Right, this is your psi b, right? This represents the amplitude, psi a and psi b represents the amplitude. So when these will overlap destructively, we get a smaller wave like this, right, whose amplitude would be equal to psi a minus psi b, right? So what would be the probability of finding the electron in this newer orbital, which is smaller compared to these two orbitals? It would be, in this wave, it would be psi a minus psi b. Why minus? Because the orbital that is obtained when these two waves meet destructively, right, we get a smaller wave. So the amplitude of that smaller wave would be the we'll get it by subtracting one bigger wave from the smaller wave, psi a minus psi b, right? Now, what if you want to draw it this way? This is 1s orbital, this is another 1s orbital, right? When these two meet, they will form a bigger orbital like this, right? This wave represents this bigger orbital. Similarly, if these two meets destructively, right, we will subtract one from the other, and what you get is smaller orbital, right, with a node between. What is this node? At this point, the probability of finding the electron is 0. You will never find electron here. So here, this orbital is spread over both the atoms, right, and these two points represents the nuclei of these two atoms. So right, so what happens in this is your BMO, bonding molecular orbital, this is your antibonding molecular orbital, right, ABMO, antibonding molecular orbital, right. So here the electrons will spend most of their time between the nuclei, right, electrons will spend most of their time between the nuclei. Here electrons will spend most of their time away from the space between the nuclei, right, so they may be here anywhere, right, but less time between the nuclei. So when electrons spend most of their time between the nuclei, since these electrons are negatively charged, so they will develop an attraction between the nuclei, right. So these electrons, what they are doing is they are holding these electrons together in this orbital, right. So when they are holding two atoms together in this molecular orbital, this leads to bonding. That is why we call it as bonding molecular orbital. And if you remember, this is your in phase orbital, the orbital that gets formed when these two waves meet in phase, and when these two waves meets out of phase, what you get is the orbital. We call this orbital as out of phase orbital, right. And here since we have attractive forces here between electrons and nuclei, attractive forces releases energy. So the energy of this molecular orbital energy is less compared to combining orbitals. Right? Energy is less. So these two orbitals, when combined, they formed molecular orbital that has lesser energy. Right? So now this explains why atoms combine to form molecules. Right? Because two systems, if they want to attain stability, right, they should lower their energy. So when these two atomic orbitals combine, they form molecular orbital that has lower energy. Right? So that is why this molecule is stable compared to these atoms. These atomic orbitals are from atoms, right? And together they form this molecular orbital that has lesser energy. Since it has lesser energy, so this is more stable compared to these atoms. Now let's look at this antibonding molecular orbital. In case of antibonding molecular orbital, since electrons are spending most of their time away from the internuclear region, right? Internuclear region is the region between these nuclei, right? So since they are away from internuclear region, so these nuclei are exposed to each other, right? They are exposed to each other. There is no shield of electrons between the nuclei. Here these electrons are acting as a shield between the nuclei, right? So here there is no shield of electrons between the nuclei, so these two nuclei are exposed. Right? Since both are positively charged, so repulsive forces will increase. Since both these are positively charged, therefore repulsive forces will increase, right? Repulsive, which will increase the energy, of the molecular orbital, right? Since the molecular orbital, this molecular orbital, which is out of phase orbital, has higher energy, right, due to high repulsion between the nuclei. So this leads to destability, right? And the energy of this orbital is high compared to the combining atomic orbitals, right? So that is why this will not lead to bonding, right? Because energy of this molecular orbital is high, so this will not lead to bonding, and since energy is higher, so this will not lead to bonding, right? And energy is lower, so this will lead to bonding, right? We'll understand this more in a minute, right? So let's draw the energy level diagram that we have constructed before. The energy level diagram was like this. This is one orbital, right? Right, and this is another orbital, right? So when these two orbitals combine in this fashion, they will form this bigger orbital that has lower energy. So this is how we will draw it, right? And this molecular orbital has higher energy, so this is how we will draw it. This represents your bonding molecular orbital. This represents your antibonding molecular orbital, right? This is your 1s, this is your 1s, right? Let's take the example of hydrogen. Say this is hydrogen. Both these are hydrogen orbitals, right? Now if you look at this, I have drawn here the smaller line. Here I have drawn a bigger line because the energy of this bonding molecular orbital is less compared to these two orbitals, right? And energy of this antibonding orbital is higher compared to these two orbitals, right? So this is what we call it as energy level diagram, in which energy increases in upward direction. Energy increases in upward direction. We will draw bigger diagrams in future, right? When we have more orbitals, we have only 1s orbital. If we have 2s 2p orbitals, so this diagram will grow, right? Till this point we are clear, and we'll introduce you to two things: the lowering of energy. This lowering of energy in case of bonding molecular orbital will lead to stability, right? So the lowering of energy of the bonding molecular orbital, then the combining orbital is stabilization energy, right? So this lowering of energy, right, here energy is less compared to the combining orbital. So here we have lowering of energy. So what we get here is a stabilization energy. Right? And here the opposite case of this, here we have higher energy, right? So here we have destabilization energy. That higher energy is your destabilization energy, right? Now let's look. We said that here in this case, when a bonding molecular orbital is formed, electrons will spend most of their time in the internuclear region. That is, which means that the probability of finding the electron is more in this molecular orbital, right? In bonding molecular orbital. We'll prove this mathematically. Similarly, in this case, the probability of finding the electron is less in the internuclear region, right? Since the probability of finding the electron is less in internuclear region, which will lead to destabilization, right? Because of repulsive forces. Here, the probability of finding the electron is more between the nuclei, which will lead to stabilization due to attractive forces between electrons and the nuclei. Or we also say that these electrons act as a shield between the nuclei, right? Which will prevent the repulsive forces between these positively charged nuclei, right? And hence leads to stability or lowering of energy. Let's solve this. Okay, we know that the probability of finding the electron in this orbital is psi a square, here psi b square. So probability of finding the electron in this bigger orbital should be higher. What we say is higher. Now let's prove this mathematically. If you solve this, what you get is this we will solve using formula a plus b whole square, a square plus b square plus 2ab. So we will get this psi a square plus psi b square plus 2 psi a psi b, right? So this is the probability of finding the electron in this bigger molecular orbital, right? Which you can see is higher compared to the sum of these two probabilities. Probability of finding the electron in this is psi a square, in this is psi b square. So if you do the sum of these, what you will get is psi a square plus psi b square, right? But when these two combined to form this bigger wave or this bigger orbital, right, whose amplitude is psi a plus psi b, or wave function is psi a plus psi b. So when we found the probability which we get from the square of this wave function psi, right, we get psi a square plus psi b square plus 2 psi a psi b, right? So here the probability is increased by this much amount, plus 2 psi a psi b. Here earlier it was, the probability was psi a square plus psi b square. Now the probability is this, right? And this term is higher by this term. I'm sorry, this term, this entire term is greater than this by, this is greater than this by 2 psi a psi b, right? So this much probability is higher, right, of finding the electron in bonding molecular orbital, right? Now if we talk about antibonding molecular orbital, now let's look into antibonding molecular orbital. Here also, if you if you sum these two, this was, I'm sorry, minus, this is psi a square plus psi b square, right? If you take square of this, psi a square plus psi b square minus 2 psi a psi b, right? Here you can see, before combining, their probability of finding the electron in internuclear region is psi a square plus psi b square, or simply we can say that the probability of finding the electron in these two waves combinedly is psi a square plus psi b square. But when these two combined to form this smaller wave or this smaller orbital that has less space between the internuclear region, or I'm sorry, what we say is, in which in this smaller orbital electrons spend less time in internuclear region, right? So the probability of finding the electron in internuclear region is less, which will lead to destability. If you look at this, probability of finding the electron is less in this case, in this smaller wave, by psi a, this is less by 2 psi a psi b, right? So now we have proved mathematically that probability of finding the electron in bonding molecular orbital is high, is greater by 2 psi a psi b, and in anti-bonding molecular orbital is less by 2 psi a psi b, right? I hope this is clear. Now we'll see another thing. Okay, one important thing, like we used to denote atomic orbitals by SPD, right? We used to denote orbitals by SPD. Similarly, we denote atomic molecular orbitals by sigma, delta, right? Sigma and delta, right? These are the notations for, I'm sorry, sigma, pi and delta. Sigma, pi, delta, right? This is for bonding molecular orbitals, right? Similarly, for anti-bonding orbital, we just put a star sign, sigma star, pi star and delta star. This is for anti-bonding molecular orbital, right? These are the notations for molecular orbital bonding. These are the notations for anti-bonding molecular orbitals, right? Now let's see some of the main features of a bonding and anti-bonding molecular orbital. We have already seen, already done this. This is formed by additive effect bonding molecular orbital. Anti-bonding is formed by subtractive effect of the combining orbitals. In bonding molecular orbital, electrons spend most of their time between internuclear region. In anti-bonding molecular orbital, electrons spend less time in internuclear region, right? And in case of anti-bonding molecular orbital, these anti-bonding molecular orbitals are represented by sigma star, pi star, right? And bonding molecular orbitals are represented by sigma and pi, right? And these bonding molecular orbitals are formed when atomic orbitals overlap head on, right? When same sign atomic orbitals, for example, if this is your p orbital plus p orbital, right? So a bonding molecular orbital will form when same orbital will overlap, right? That is, plus of this orbital will overlap with plus of this orbital, right? These two are atomic orbitals. They will combine and form a molecular orbital, right? By head-on overlap, right? An anti-bonding molecular orbital will form when plus of this will overlap with minus of the other orbital, right? This is the difference between the two. So conditions, there are certain conditions for the formation of atomic orbitals. They should have proper orientation. The conditions are the combining orbitals should have comparable energies, that like why we were doing at the time of what we did when we did overlapping of atomic orbitals, it's same, right? Here also, right? I'm just rubbing this. So conditions for the formation of atomic orbitals. The first is they should be of comparable energies, right? When we say comparable energies, 1s will combine with 1s, right? Not with 2s, right? Or 1s will combine with 1p, right? That is, they should have similar energies, right? They should have comparable energies, right? So 1s will combine with 1s, I'm sorry, there is no 1p, I'm sorry. 1s will combine with 1s, similarly 2s will combine with 2s, or 2s will combine with 2p, right? This is what it means. That is, the combining orbitals should have comparable, almost same energy, right? 2s will not combine with 1s. Why? Because their energies are not comparable. 2s has higher energy, 1s has lower energy. The second condition is they should have proper orientation. When atomic orbitals combine, they should combine in proper orientation, right? Proper orientation, right? That is, 1s will combine with 1s, right? And 2s will combine with 2s, and s orbital can combine with p orbital like this, right? S can combine with p. Similarly, px of one atom, when we talk about heteronuclear atoms, molecules, I'm sorry, px can combine with px, right? And py can combine with py, and pz can combine with pz orbitals, right? And px will not combine, px will not combine with py, right? And py will not combine with pz, right? This is how it works. So they should have comparable energies and proper orientation, right? And types of molecular orbitals formed, right? So the wave functions of two 1s orbitals can combine in two different ways, right? If we have, like, they will combine with same signs, right? When atomic orbitals combine or overlap to form molecular orbitals, there are two ways it will happen, right? So the two ways are, right, plus of this will combine with plus of this, right, to form a bigger orbital like this, right? This is your constructive interference. The other way is plus of this will combine with, if suppose it combines with minus of this, it will form a smaller orbital with a node between, right? This is your antibonding molecular orbital. This is your bonding molecular orbital, right? Now let's look at, suppose let's take 2pz orbitals like this, right? When these two combine, plus of this, right, will combine with plus sign of this. When these two orbitals overlap, 2pz with 2pz, right, it will form a bigger orbital, right, of this type. When plus of this lobe will overlap with plus of this lobe, it will form this sigma orbital, sigma orbital. This was also sigma orbital. By these are formed